Hello dear students, in today's lecture we will discuss what is called as the fluid theory of plasma. So, if you are familiar with the single particle theory of plasma, we have studied that plasma can be treated as a single particle or a fluid. In order to understand the motion of plasma or the behavior of plasma or various properties of plasma, we can treat plasma as a single particle. We have, and then we can treat the plasma as a fluid, or we can also understand by using statistical methods, statistical entity, by treating plasma as a statistical entity, right. So, single particle theory of plasma helps us understand how the plasma will behave in the presence of external electric, magnetic or gravitational fields. Sometimes it may not be appropriate to treat the entire plasma as a single particle. Most of the times, the basic reason for departing away from this single particle theory towards the fluid theory of plasma is that the type of electric magnetic fields or electromagnetic fields are generally assumed, or even they can be called as prescribed in the case of plasma being treated as single particle. But in general, the electromagnetic fields are not prescribed, rather the plasma, by the virtue of its motion, by the virtue of its charge concentration, as the plasma moves from one point to another point, each particle, let us say you have electron and ion, each of these electrons and ions, as they move, they will generate currents, and subsequently these currents will be responsible for the generation of magnetic fields and let us say electric fields, right. Now, these secondary magnetic and electric fields which are created by the virtue of plasma's movement will obviously try to alter the way plasma is moving. So, it is a highly dynamic concept in which the cause of electrons and ions moving in a particular direction will try to create electric and magnetic fields which will influence the motion of the plasma particles. So, if these fields have to be created, then the electrons and ions, each of these electrons and ions should move in such a way that the electromagnetic fields thus created should allow these particles to move the way they were moving originally, right. So, this is you have to have a self-consistent picture in which one aspect will reinforce the second aspect. So, electromagnetic fields are created, they should allow the plasma particles to be moving as the way they were moving earlier, right. Now, in order to have a physical description of this process, we need to have some sort of equations which can build the gap. So, if the plasma is having certain velocity, certain mass and all that, we should be able to compute the resulting electromagnetic fields. If we know the strength of these electromagnetic fields, or if we know the analytical expressions which can describe the movement of this plasma, it may be possible to be able to write the position of these particles as a function of time, or we will be able to understand the time evolution of plasma particles. But in reality, it may be possible or it may be feasible to complete this complete the understanding of this process for very limited number of particles. But if you have particles of the order of, let us say, 10 to the power of 12, for instance, per unit volume, then this problem will become immensely difficult to handle with existing mathematical or computational methods. But most importantly, we need not worry so much about this, but because nearly 80% of the plasmas can be treated or can be understood, their movement, their processes and their physical effects can be understood by treating the plasma as a fluid. fluid. So 80% of the plasma processes can simply be understood, or 80% of the plasmas can be understood by treating them as fluids. So how is it going to be different? So if you can familiarize yourself with the understanding of single particle theory of plasma from any of the earlier lectures, either in this course or the other courses. But once you realize that by treating the plasma as a single particle, what and all you can do, then we will realize what is the practical extent of treating plasma as a particle, right? Now, in this class and subsequent classes, we will try to see what are the different physical laws which we have to be familiar with, or what are the governing equations which we need to know so that we can describe plasma as a fluid, right? So, this fluid theory of plasma or fluid description of plasma is very important for understanding the plasma flow, plasma movement from one point to another point, especially in the context of the solar terrestrial physics, because we have a continuous stream of plasma particles reaching the Earth from the Sun. The entire course basically tries to give a solid foundation on understanding various aspects related to this interaction of solar wind particles or solar wind plasma with the terrestrial atmospheres. Let's say, for example, the case of planet Earth, or the case of Mars or Venus, etc. Right. Now, if you want this description to hold, generally we need to have some governing equations. What are governing equations? Governing equations are those set of equations which can help us in understanding the physical properties of a particular system. So, if you want to understand the thermodynamical properties of a gas, you need to know the ideal gas laws and associated laws, which can all form a set of equations, and the description of this physical system can only be done with the help of physical parameters. So, these physical parameters are naturally going to be the variables in these equations, and as a general rule, we solve these equations to get the values of these variables, or in some cases it may be possible that you can understand the empirical relation between any two variables by using certain set of equations, right? So, that is very easy to understand what is the role of governing equations and how governing equations can help us understand the time evolution of any physical system. All right. Now, in this case, coming to the fluid description of plasma. Now, plasma, as we know, plasma is an electrified gas. So, plasma is, of course, a gas, and it can also exhibit electric and magnetic properties. This is very important. So, now we should be able to combine the laws of electrodynamics with the laws of thermodynamics, so to say. Only then we will get a description or set of equations which will be sufficient to understand the description of plasma, the movement of plasma, right? Now, in rigid body dynamics, most of the times we identify the system or the object or something of the concern for our understanding with a specific mass to begin with. Mass, and if it has a mass, it has a velocity, it has an acceleration, it is being acted upon by a force. Then, if you know all these, let's say 4 fundamental variables, you can understand how this mass will move as a function of time, how this mass will get under the influence of these forces, etc. Right? But in fluid dynamics, or in this case plasma as a fluid, what we do is we define an imaginary volume, or called as a control volume. Control volume can be called as a hypothetical entity inside the fluid on which you are going to apply the physical laws. For example, if you define something to be of a volume delta V, a control volume, then you can apply the laws of conservation, law of conservation of let's say number 1 mass, law of conservation of energy, law of conservation of momentum, etc., to get the governing equations. Right. So let us just look at the flow of things that we have understood so far. So the single particle theory of plasma cannot be a generalized theory of plasma. It has some limitations. Then we realized by simply treating plasma as a fluid, 80% of the plasmas can be easily understood. Now, if you want to talk about this understanding aspect of plasma, we need to have some set of governing equations which we can obtain by treating plasma to be represented by a control volume. And once you define this control volume and attribute a volume delta V to it, we are going to apply the laws of conservation of momentum, mass and energy, etc., onto this control volume and get this full set of governing equations. This is the basic flow that we have understood so far. Now, speaking about this control volumes, there can be two different types of control volumes. One, an Euler or Eulerian control volume. Another, a Lagrangian control volume. All right. So, what is the difference? So, if you have a system of plasma, you have a, let us say you have a chamber filled with plasma. We assume a small entity of mass delta V and a density rho. Mass is implicitly there in terms of these two variables, right? Now, this is the control volume that I am talking about. Okay. Whatever the conservation law that I have to apply, I will apply onto this control volume, and I will assume that this law that I am going to get, this equation that I am going to get, is pretty much valid for the entire system itself. Right. Now, that is the basic idea of the control volume. If you have to understand why I have two different types of control volume, one, an Eulerian control volume is the one in which actually moves along, okay, which can move from one point to another point. So, the Eulerian control volume is the one which is fixed with respect to the coordinate system x, y, z. This is not going anywhere. Okay. Rather, we expect the fluid to rather go through it. Okay. On the contrary, the Lagrangian control volume is the one which is basically defined as an identified mass of particles with a mass delta m. In this, fluid is, of course, fluid is there, but this control volume is going from one place to another place. Okay. So, in both this is the basic difference between these two control volumes, right. So, we will choose these control volumes as per the purpose and the problem that is there to understand. Okay. So, that is the basic difference, right. Now, once we do this, then why are we doing this? Because we are treating plasma as a fluid. See, fluid is a very difficult thing or a very different thing as such in comparison to a rigid body. Okay, because fluid's motion is governed by a completely different set of equations. Right? Of course, these set of equations are usually found in fluid dynamics, but since we are dealing with a fluid which is electrodynamical in nature, which has an ability to be influenced by the electric and magnetic fields, we have to cleverly combine the laws of electrodynamics with the laws of fluid dynamics, right? So that combination is what is going to give you the magnetohydrodynamics or a simple approach to understand plasma, right? Now, in addition to this, something is more important. To start the fluid dynamics, we have to understand what is a total derivative. So, total derivative is not something that you may not have heard before in your differential calculus or in your differential equations lessons. You must have already come across what is a partial derivative and what is a total derivative. In the context of a fluid, generally it is important. Let us consider this control volume. Okay, let us consider this control volume. Now, this control volume is existing at certain coordinates. Let us call the set of coordinates as x naught, y naught, z naught, t. Right. Now, this control volume encompasses certain plasma inside, and this plasma will have certain physical properties or physical measurables. Let us say, for example, density, temperature, anything like pressure, volume, chemical potential, or etc., any physical parameter. So, if you have a measuring equipment, you can carry out a measurement within this control volume and you can establish what are these values at a particular instant of time t1. This is more important, right? Now, as the time evolves from t1 to t2, what happens? You would naturally expect these variables to change. Okay. If you have a situation wherein this volume is not exchanging anything with the surroundings, if you have a perfectly adiabatic nature, adiabatic picture, you would expect that these variables will remain constant for the time to come. But what happens is, if this volume is fluid and if it has a tendency to move from one point to another point, okay. Now, if this volume is going from one place to another place, let us imagine the physical parameter that I am trying to see is rho, density which is within the volume, within the closed enclosure or within this cuboid, right. Now, as this entity, as this control volume that I am talking about moves from one place to another place, what happens? So, there can be a change in the density because of because the position coordinates have changed. It may have moved to a different place where the ambient thermodynamical conditions which can influence the density may have changed. As a result, the control volume may have expanded or may have shrunk, leading to a density which is different from the original density, right? Or, for example, now this change which is from delta rho, let us say we call it as delta rho, which is basically rho 1 minus rho 0. If you don't know that this control volume has traveled from one point to another point, if you don't know that, if you're not conscious of this control volume's movement, you would expect that this change in the density is only because of the time that has elapsed. So, as the time progressed, the density has decreased or increased, right? Now, but if you know how this density change has come into the picture, then you would track the movement of the control volume, right? Now, this derivative that I am talking about is generally represented with a capital D over dt, change with respect to time, capital D, accounts two different things. Two different things. One, change in the physical parameter, change in physical quantity with respect to time, change in physical quantity with respect to time. And second is change in physical quantity with respect to space. Or what is the physical quantity? Any physical quantity which is under consideration, right? So, we have these two things. Generally, partial derivative, how do you evaluate partial derivative? You evaluate the partial derivative of a variable with respect to an independent coordinate while keeping all other independent coordinates constant, right? Now, we will try to see how these two things can be combined. So, a simple example could be, let us assume this control volume okay. So, this is the control volume and the measurable quantity inside is density, like I said, and this control volume is situated in a thermal gradient. Okay, let us say have a gradient like this. So delta T, del T is the thermal gradient. So del T is in this direction. Okay, that is as you go along the positive y axis, the temperature will increase. So you have x, y and z. As you go along the positive y axis, the temperature will increase, right? Now, so initial coordinates of this control volume are x0, y0, z0 at t0. After a certain period of time, certain amount of time, it occupies a new space and time coordinates. It is situated here, which are x1, y1, t1 and z1, right? Now, there are two things here. One, the density must change as it is traveling along the thermal gradient. So, density change not only occurred because of its displacement from one point to another point which is at a larger temperature. It can also be seen that just because this control volume is moving along the time t0 to t1, you can say that the density change d rho by dt is a function of densities change with respect to x, with respect to y, with respect to z and with respect to time. Right. Now, let us try to bring it in a way that we can write some expression for that. Let us say we assume the temperature to be the physical quantity that is under consideration. Okay. Now, this derivative that I am talking about is, like I said before, is called as the total derivative, or this is also called as, so like I said, this derivative is accounting for change of a physical quantity following, this is very important, following the motion, or along the path. Now, the local derivative at any fixed location is dou by dou t. Now, since we have already defined the control volumes, so this local derivative, let us call this as the local derivative, in contrast with our understanding of total derivative. This is the local derivative or Euler derivative, right? Because this is not moving anywhere, Euler derivative, this is there. But when you take capital D by dt, which we are going to be calling as the total derivative, and this can also be called as a Lagrangian derivative. All right. So, let us take a particular physical quantity, temperature, which is just a variable, any variable we can consider instead of that. Okay. So, here, since we are talking about a Lagrangian derivative, the position coordinates x can change with respect to time. So, we make the position coordinate x to be dependent on time, the position coordinate of the control volume, y can also change with respect to time, that is why we keep it as y also a function of time, z can also change with respect to time. So, that becomes z as a function of time and the time itself. So, if you have understood it clearly, so x, y, z are the position coordinates of the control volume. Since we are taking a Lagrangian control volume which can move anywhere within the fluid. So, the position coordinates which define this control volume's intermediate or instantaneous position will keep varying as a function of time. So, that is why I made x, y and z as a function of times. Right. Now, this temperature that we were taking as a variable becomes a function of x, y, z and t. What does it mean? So, at different points in space and time, the temperature can be different inside the fluid. Right. So, that means temperature is of course going to change. So, from one point to another point. Okay. So, in that case, what we do is, let us say now the control volume, the Lagrangian control volume, we assume that initially it is occupying the coordinates x naught, y naught, z naught, t, which will after certain point of time, they will be x naught because of the motion of the control volume. The new set of coordinates are going to be x naught plus delta x plus y naught plus delta y, z naught plus delta z and t naught plus delta t. Right. Now, obviously, you would expect the temperature to be changing along this displacement. So, change of temperature, the intermediate change of temperature delta T can be written to accommodate this displacement as dou T by dou x times delta x plus dou T by dou y times delta y plus dou T by dou z times delta z plus dou T by dou small t, temperature change with respect to the temperature, time times delta t plus higher order terms. Right. Now, we can always neglect these higher order terms because they will bring a very small fraction of the variability of temperature with respect to the space coordinates. Now, so this is, what is delta T? Delta T is a change in temperature. Delta T is a change in temperature with respect to x, y, z and t. Okay. We will take this derivation ahead and obtain an expression for the total derivative capital D by dt, which can operate on any physical parameter in the next lecture.